89 degrees Celsius. Inside the rock, not the air, the rock itself, and someone decided to drill a railway through it. Welcome back to the channel. Today we are looking at one of the most audacious infrastructure projects ever attempted in human history. Not the longest, not the most expensive, the most hostile, the Sichuan-Tibet Railway, a 1629-kilometer line connecting Chengdu, a city sitting at roughly 300 meters above sea level, to Lhasa, the capital of Tibet, sitting at roughly 3,000 meters. That difference in elevation more than 3,000 meters from start to finish is just the beginning of the story. This is not just a train line. This is a 1629-kilometer act of defiance against geology. Gravity, altitude, temperature, seismic instability, and the very laws of what infrastructure is supposed to be able to do. This is a railway that for most of its most difficult section does not touch the ground at all. It flies through mountains. It buries itself beneath rivers. It suspends itself over gorges, so deep the bottom disappears into cloud. And it does all of this on terrain that has been actively trying to destroy it since before a single drill bit touched the surface. Because you need to feel what the builders were up against before you can understand what they built. 90% of this entire route sits above 3,000 meters above sea level. At that altitude, the human body does not work normally. Oxygen is thin, breathing is difficult, sustained physical labor, the kind required to build a railway, becomes dangerous. Not uncomfortable, dangerous. Then there is the geology. This railway crosses more than 40 major tectonic fault lines. More than any previous railway project on Earth, the Indian tectonic plate is pressing northward into the Eurasian plate at roughly 40 millimeters per year. That movement is what created the Himalayas. It is still happening. Right now, the ground here does not sit still. It shifts, it heaves, it collapses. Earthquakes are not rare events in this corridor. They are a regular feature of the landscape. Then there's the heat, not the heat of the sun, the heat of the Earth itself. In certain tunnel sections, geothermal energy heats the surrounding rock to 89 degrees Celsius. That is hotter than boiling water, hotter than the point at which water turns to steam. And workers were drilling through it. More than 70% of the workforce on the tunnel sections reported physical symptoms, chest pain, loss of consciousness, vomiting. Directly linked to the heat conditions underground. That figure comes from a study by Professor He Chuan of Southwest Jiaotong University. This was not a secret. It was a documented crisis of human endurance. Then there is the terrain itself. The route crosses 14 major rivers. It passes over 21 snow-capped mountain peaks. It accumulates more than 16,000 meters of total elevation change across 8 full ascents, rock falls, active fault rupture zones, and they decided to build a railway through all of it. Before we continue, if this is the kind of deep engineering breakdown you come here for, make sure you hit subscribe right now and stay with us until the end. Because what passengers will experience when this line opens, a smooth 13-hour ride from Chengdu to Lhasa, hides something almost no one knows about. The gap between what riders will see and what actually holds this railway together is extraordinary. We'll get there. At first there was nothing here but raw landscape, no infrastructure, no road worthy of the name, no rail of any kind connecting Chengdu and Lhasa through this corridor. Just gorges and glacier and fault lines and rock hot enough to cook with. The existing rail connection between the two cities ran via the Defying Tibet Railway, a different longer route, and that journey took around 48 hours. The drive through the Sichuan-Tibet highway, when conditions allowed it, took closer to 3 days, and those were the good options. This particular corridor, the direct route through the mountains, had been studied, dreamed about, and quietly shelved for decades, because every time engineers looked at it seriously, the answer came back the same. It cannot be done. Not yet. Maybe not ever. Here is why every obvious solution fails. If you try to build a conventional surface railway through these mountains, the gradient kills you. Trains have hard physical limits on how steep a slope they can climb. The terrain here rises and falls with a violence that no standard track geometry can accommodate. The slopes are too steep. The curves are too sharp. If you try to lower the cost by routing around the worst sections, you add hundreds of kilometers and encounter different versions of the same problems. Avalanche risk here, active fault there, river flooding season somewhere else. If you try to build surface roads instead and move freight by truck, you already know the answer. The Sichuan-Tibet Highway exists. It is dangerous, it is slow, it closes regularly, it cannot carry what a railway can carry, and if you try to fly, well, flying does not move the volume of goods and people that a region of this scale needs to develop economically. So the engineers came back to the railway, and this time, they did not route around the problems. They went straight through them. The solution was not a railway in the conventional sense. It was a system, a layered, interlocking engineering system where every component was designed to work with every other component because any failure in any single layer would cascade through the rest. The answer to impossible terrain was not to avoid it. It was to go underground and overhead simultaneously. Tunnels where the mountain could not be climbed. Bridges where the valley could not be filled and where the two met, which was nearly everywhere, on the hardest section. A railway on the most challenging section of this line, the stretch running approximately 1,011 kilometers between Ya'an and Nyanqi, roughly 94.8% of the entire route, is composed of either tunnels or bridges. Think about that number for a moment. In the most difficult part of this journey, less than 6% of the track rests on ordinary ground. Every other meter is either floating in the air or buried inside a mountain. The first work that happened was not drilling. It was not pouring concrete. It was reading. Years before a single tunnel boring machine was switched on, survey teams went into this terrain to understand it, and understanding this terrain, teams had to map fault lines, measure ground temperatures at depth, calculate seismic risk zones, model the behavior of permafrost under load, chart flood patterns for 14 major river systems, assess avalanche corridors, and model how the ground would move, not if but how during the inevitable earthquakes that would strike during and after construction. Every measurement mattered. Every geological reading mattered. Because building a tunnel in the wrong location here did not mean inconvenience. It meant catastrophe. The data, collected in those survey years, shaped every decision that followed. Where to tunnel, how deep, at what angle, with what materials, with what cooling and drainage and ventilation systems, and how to keep the whole structure alive when the earth around it shifted. Then came the groundwork. Before any primary structure could go up, the teams had to prepare the surface. This meant clearing unstable material across vast areas. It meant anchoring slopes that would otherwise slide. It meant building access roads to locations that had no roads, roads that were themselves engineering projects, carved into cliff faces and suspended over drops. Every kilogram of equipment, every liter of fuel, every bag of cement for the early access infrastructure had to be moved into terrain that did not want to be entered. The construction crews were not just building a railway, they were first building the ability to build a railway, and the tunnels are where this project truly separates itself from everything that came before it. There are more than 70 tunnels on the Nyanqi section alone. The longest exceeds 40 kilometers in length. To drill through 40 kilometers of mountain, through rock that in certain zones is hotter than boiling water, through geology that crosses active fault lines, they had to use many, chosen differently for each section based on what the survey data said the mountain would tolerate. In zones where the rock was stable and the temperature was manageable. Massive tunnel boring machines, enormous cylindrical devices that grind forward through solid stone, were deployed, rotating cutting heads, dozens of meters across, lined with hardened steel disc cutters, advancing slowly through the mountain, while simultaneously installing precast concrete tunnel lining segments behind them. The cutting head needs the hydraulic system. The hydraulic system needs the ventilation. Without any one of them, the machine stops. With all of them working together, it moves forward, sometimes only centimeters per h. But it moves in zones where the heat was extreme. Where the geothermal rock temperature reached 89 degrees Celsius, tunnel boring machines could not function safely. The operators cannot survive without extraordinary protection. In these sections, the crews shifted to a different method. Drill and blast. This is an older technique, but it is the only one that works in conditions this severe. Workers drill arrays of boreholes into the rock face, load them with precisely calculated charges, retreat, detonate. In a superheated tunnel, this process happens in short rotations. Workers go in, do what they can, in the time their bodies allow, and come out. Then the next team goes in. Every shift mattered. Every minute inside mattered. and more than 70% of them were suffering physically as they did it. The heat was not the only enemy inside the tunnels. The water was equally brutal. Some tunnel sections broke into underground aquifers, pressurized water systems under the mountain that burst into the tunnel face with enormous force. Managing that water required waterproofing systems, drainage channels, pumping infrastructure, and lining materials capable of resisting constant hydrostatic pressure. The tunnel lining itself, the concrete shell that defines the interior of the finished tunnel, had to be designed not as a static structure, but as a living one. It had to flex with the mountain. It had to accommodate seismic movement without cracking. The concrete mix was engineered specifically for this environment, resistant to heat, resistant to chemical attack from the minerals in the rock, resistant to the kind of slow deformation that happens when rock under enormous pressure gradually closes in around a void. Every joint in the lining mattered, every drainage outlet mattered. Because the alternative, a tunnel that fails, is not just an engineering problem. At depth, under a mountain with a railway running through it, a structural failure is catastrophic and possibly irreversible. Then came the bridges. If the tunnels are the buried heart of this railway, the bridges are its visible miracle, and they are numerous. On the 9-km Lhasa section alone, one segment of the full line, there are 121 bridges. The river at the core of this landscape, the Yarlung Sangpo, is crossed 16 times on that segment alone. 16 times the same river. Building a bridge over a Tibetan gorge is not like building a bridge over a river in a flat country. The gorges here drop hundreds of meters. The river at the bottom is wild. The winds at height are unpredictable. The foundations cannot be set in soft or unstable ground. They must reach down through whatever loose material sits on the surface and anchor into bedrock. And the structure above must handle not just the static weight of a loaded train, but the dynamic forces of that train moving at 160 to 200 kilometers per h/r, the wind loads at elevation, the thermal expansion and contraction across a temperature range that can swing enormously between seasons, and the seismic forces. The construction sequence for each bridge followed the same layered logic as the tunnels. First, site the foundations, then build the piers, the vertical columns that carry everything above. Then construct the deck, the horizontal platform the track will sit on. Then install the track itself with its precise tolerances, its continuous welded rails. The piers for bridges crossing the deepest gorges are themselves enormous structures, sometimes dozens of meters tall, built from concrete that had to be mixed on site using locally sourced materials where possible, because transporting bulk materials to these locations was itself a logistical project. The connections between the bridges and the tunnels on the entire line, where a train exits a tunnel and immediately enters a bridge, or the reverse. The transition must be seamless. The track alignment must be perfect. The drainage must work in both directions. The structure must handle the sudden change in environmental condition. The humidity, temperature, and wind exposure all shift dramatically. From inside a tunnel to outshift, every millimeter of alignment mattered. Every drainage gradient mattered. Every expansion joint between the two structure types mattered. Then came the track itself. And this is where most people stop thinking about what they're re-looking at. Track, to most observers, is just rails on sleepers, on ground. But on a railway like this, the track is an active system. The rails are continuously welded. No gaps, no joints, a single seamless length of steel that expands and contracts as one piece with temperature changes. The sleepers are not wood. They are pre-stressed concrete, engineered to distribute the dynamic load of a passing train across the widest possible contact area. The ballast, the crushed stone the sleepers sit in, is graded to a precise specification, compacted to a precise density, drained to a precise standard. On bridge decks, the track transitions to a slab track system. Rails fastened directly to a concrete deck, because there is no room for ballast on a surface that must also manage drainage. The switch systems at junctions are heated electrically, because at altitude, ice forms and a frozen switch is a stopped railway. Every component in the track system has a calculated lifespan, a maintenance interval, a failure mode. Every component was chosen knowing the conditions it would face. Before a single revenue passenger was placed on any section of this line, trains ran, not passenger trains, test trains, weighted to simulate full loads, running at low speed, then at design speed, then beyond design speed, looking for resonance in the bridges, settlement in the tunnel floors, movement at the track joints, vibration in the overhead catenary system that feeds power to the electric locomotives. The overhead catenary, a precisely tensioned wire system suspended above the track, had to maintain its geometry within millimeters at all temperatures, all wind speeds, all train speeds. Testing teams recorded every deviation. Engineers returned to adjust every element that did not perform to specification. This process happened first on the Chengdu Ya and section, which opened on the 28th of December 2018. Then on the 9-key Lhasa section, which opened on the 25th of June 2021. Each opening was not just a ribbon cut. It was the end of a cycle. Survey, prepare, build, test, adjust, certify. And a new cycle began, the long section in between, the hardest section, the one with the superheated rock and the 40 fault lines and the 94.8% tunnels and bridges, which is still being built. The project as a whole began in 2014 and is expected to be completed around 2030. The total estimated cost is approximately 320 billion yuan, roughly 45 billion US dollars. Most passengers, when this railway eventually opens its full length, will board at Chengdu and arrive in Lhasa. They will sit in a climate-controlled car. They will watch the landscape pass. They will perhaps sleep. They will not see the 89 degrees Celsius that the rock reached when the tunnels were being cut. They will not see the moment a tunnel face broke into a pressurized aquifer and water exploded inward. They will not see the workers rotating through superheated tunnel sections in short shifts because extended exposure meant collapse. They will not see the 47 tunnels and 121 bridges of the 9-inch section because those will pass too fast. In darkness and then in light, in darkness and then in light, the rhythm of emergence and submersion that defines this railway. They will not see the 16 crossings of the Yarlung-Tsangpo. They will not see the more than 40 fault lines crossing beneath their wheels. They will not see the 16,000 meters of total elevation accumulated and surrendered across 8 ascents and descents over the length of the journey. They will not see the years of survey data that determined every curve, every gradient, every location where a tunnel portal was placed. They will not see any of it. And that is perhaps the most profound achievement of all, that something this violent to build can be this smooth to experience. This railway, this is a feat of will applied to knowledge. It is what happens when a civilization decides that a thing must exist and then refuses, methodically and at enormous human cost, to accept that it cannot. The mountain pushed back. It pushed back with heat and water, and earthquake and altitude, with a different drill bit, with a different concrete mix, with a different approach for a different fault, with another short shift in a hot tunnel, with another test train on a new bridge, with 16 years of work and approximately $45 billion, with ours, and more human effort than any completed structure can fully communicate. This was not an infrastructure project. This was an argument with the earth. And the engineers, the construction crews managed by China State Railway Group, designed by China Railway Iriwan Engineering Group, are winning it. 1 kilometer at a time, 1 tunnel at a time, 1 crossing of a wild river at a time. When the final train rolls, the full 1629 kilometers from Chengdu to Lhasa, it will carry people over a distance that once took 3 days and now takes 13 hours. It will carry freight that once had to be airlifted or trucked at enormous expense over dangerous roads. It will carry a connection between 2 parts of a country that geology had kept separated for all of human history, and none of the passengers will have to feel the heat of 89-degree rock to get there. They will just arrive. 13 hours, smooth, safe, on time. That is the miracle. The engineering is extraordinary. The miracle is that the passengers will never know how extraordinary it is. They will only know they arrived. If this breakdown of one of the most challenging construction projects ever undertaken gave you something of fact you didn't know, a feeling you didn't expect, subscribe to the channel. Every week we go deep into the projects that built the world. Tell us in the comments, which part of this railway challenged you most? The heat? The fault lines? The sheer mathematics of 94% tunnels and bridges? We want to know. Thank you for watching.